All right, you brainiacs, buckle up, because this deep dive is going to get seriously weird, like seriously fucking weird.
We're gonna get quantum.
It is. We're talking quantum computing, but like, before you check out thinking, not this shit again, trust me, this shit's wild.
It's about understanding what these quantum computers can do
They're freaks.
that your everyday computer just can't. And like, let me tell you, it gets kind of mind-blowing.
You're telling me. So we dug up some research.
Yeah.
And this research throws classical computers and quantum computers in the ring for like a good old-fashioned math smackdown.
Yeah.
And they're focusing on these things called matrix algebra problems.
That's right. It's less about the computers themselves and more about how they handle specific mathematical functions.
So we're not talking like your everyday addition and subtraction here.
No. We're talking like hardcore math.
Hardcore spreadsheets on steroids.
They looked at classical computers, which we all know and love, are reliable but kind of boring workhorses.
Yeah.
And compared them to these like sleek, super-powered quantum computers.
Yeah. And let's be real. Sometimes it's a total knockout.
Oh, yeah.
And sometimes it is like watching paint dry. But like what blew my mind was how even the simplest math problems can expose the difference between these two computing beasts.
Absolutely. And that's what's so interesting about this. Take something as basic as, a monomial, just a variable raised to a power, like x squared. You remember that from high school, right?
Please don't make me think about high school math.
Point taken. But the thing is, when these monomials get tangled up with huge, complicated matrices, classical computers start to sweat. They slow down, they get glitchy, they might even just straight up crash.
Yeah. Like, I can't deal with this shit.
Exactly.
But quantum computers,
bring it on.
they're like, give me more of that.
Yeah, more monomials, please.
Our sources showed that they handle these complex monomial problems like way more smoothly. It's like they're speaking a different language.
Well, they kind of are. It's called superposition, and it lets them explore multiple possibilities at once, which is something classical computers can't even comprehend.
Okay, that's badass.
Right.
But it's not all sunshine and rainbows for our quantum buddies, right?
Not exactly. The researchers also looked at these things called Chebyshev polynomials.
Chebyshev polynomials.
Yeah.
That's like a mouthful of something I'd order at like a fancy cocktail bar.
Right. And these Chebyshev polynomials are like the heavyweight champs of the math world. They're a challenge for both classical and quantum computers, but in very different ways.
Yeah, those Chebyshev polynomials really threw a wrench in the works. They showed that even with quantum computers, some problems are just inherently difficult, no matter how much computational power you throw at them.
And that brings us to a really crucial point. How we access the information inside these giant matrices matters just as much as the type of computer we're using. It's like you could have all the tools in the world, but if you can't find them, they're useless, right?
Okay, I feel personally attacked. My organizational system is in development.
Don't worry, we've all been there, but think of it like this. Imagine you need a specific book from a library, right?
Yeah.
In one scenario, it's neatly categorized and easy to find. That's like having sparse access to information. Everything's where it should be.
And in the other scenario, it's buried under a mountain of like old newspapers and dirty clothes.
Right. Empty pizza boxes.
Yeah. It's like having no structure, pure chaos.
Exactly. And just like finding that book in a messy-ass room, if you can't organize information, it can make solving even simple problems insanely difficult.
Especially for our classical computer buddies.
They're just like, they're done. They're like, I can't find it, man.
It's not my fault.
It's not my fault. I'm just a computer.
So even if the problem itself isn't that complicated, if the information's all over the place, our classical computer is basically screwed.
Pretty much. It's like trying to win a race with a flat tire. Like, you might have the potential, you might have the engine, but you're not going anywhere fast.
You're going to have a bad time.
And that's why the researchers explored different ways of organizing information. They found that if we arrange it in a very specific way, using something called the Pauli basis, it can make a huge difference.
Okay, break that down for me. What the hell's the Pauli basis? It sounds intimidating.
Okay, so imagine instead of that messy-ass room, we organize all the books using the Dewey Decimal System.
Right.
That's kind of what the Pauli basis does for quantum information.
Interesting.
It provides a structured framework that makes it easier to access and manipulate the information stored in those quantum bits. You know those quantum bits? We call them qubits.
Yeah, the qubits. Those are like the building blocks of quantum information, right? Like the bits in a regular computer, but way cooler.
You got it. but way cooler because they can be in multiple states at the same time. Anyway, so by using this poly basis, some problems that were impossible for classical computers suddenly become solvable. It's like finding a secret cheat code for the
Dude,
universe.
that's amazing.
Right.
So, like, the polybasis is like our secret weapon.
Mm.
But you said earlier it's not a magic bullet. There's still some problems that even it can't crack.
True, true. It's not a cure-all. And this is where things get really interesting. The research highlighted that it's not just about the type of computer or how the information is organized, it's about the nature of the damn problem itself. Like, some problems are just inherently harder to solve than others, even if they seem similar on the surface.
They're just assholes.
They're just assholes, yeah.
Some problems are just asshole. It's like that saying, you can lead a horse to water, but you can't make it do a triple backflip.
Okay, that's a weird analogy, but I get what you mean.
You get what I mean?
Yeah. Some problems are just inherently more complex, even for a quantum computer.
So how do we even begin to figure out which problems are solvable and which ones are going to make our computers cry?
Well, that's what the researchers dug into.
Yeah.
And they found that things like how much time we have to solve a problem and how much error we can tolerate in the answer can be the difference between a problem being solvable by either a classical computer or a quantum computer, or being completely impossible with our current technology.
Oh, wow.
Yeah.
So it's like, even if you've got the fastest car in the world, you still need to consider traffic and road conditions.
Exactly. It's not just about raw computational power. It's about understanding the specific quirks and limitations of the problem itself. And this is especially true when we're talking about, like, simulating how systems change over time.
Okay.
Like modeling a complex chemical reaction.
Right.
Or predicting the weather. This is where quantum computers really have the potential to be game changers.
Because they can handle so much more information at once.
Precisely. They can explore a mind-boggling number of possibilities simultaneously, which is crucial for these kinds of simulations that would take classical computers an eternity. But, and this is a big but,
There's always a but.
there's always a but, even with quantum computers, errors are a huge pain in the ass.
They're little bitches.
They're the worst, and even small errors can snowball
Yeah.
and just completely screw up the results, especially when we're dealing with really, really complex problems. So the researchers found that managing these errors is essential if we want to unlock the true potential of quantum computing.
So it's like quantum computers, they're the hotshot race car drivers.
Yeah.
But they need a really good pit crew to keep them from spinning out of control.
Exactly. And that brings us to another really juicy tidbit from this research. Matrix inversion.
Matrix, say what now? Is this going to turn me into Neo from the Matrix?
Okay, hold on.
Because if it means I can dodge bullets, I'm in.
Not quite, but it is pretty damn cool.
Okay.
Matrix inversion is this fundamental operation in linear algebra, and it pops up everywhere. Engineering, finance, machine learning, you name it.
Okay, so we're talking real-world applications here.
Real-world application.
This isn't just theoretical mumbo-jumbo.
Exactly. This is the real deal. And what's fascinating is that quantum computers have the potential to perform matrix inversion way faster than classical computers, especially when we're dealing with massive, massive data sets.
Okay.
But here's the kicker. The complexity of this whole matrix inversion thing is linked to something called the condition number of the matrix.
Condition number. Is this like a credit score for matrices?
It's like a credit score.
Okay.
Because if so, some of these matrices need to get their shit together.
Yeah, they really do.
It's not about credit scores, but it does tell us how sensitive a matrix is to small changes.
Interesting.
So a high condition number means the matrix is more delicate, more prone to errors, harder to work with.
So if a matrix has a high condition number, it's basically a drama queen. And even quantum computers are going to have a hard time dealing with its shit.
You got it. That's one way to put it. The researchers found that even a quantum computer might struggle to invert a matrix if its condition number is through the roof. It's like trying to walk a tightrope during an earthquake.
All right, so we've got these like mind-bending quantum computers that can potentially solve problems in seconds that would take classical computers like millennia. But they also come with a whole new set of headaches, errors, sensitivity to the tiniest changes, and the fact that some problems are just inherently messy. Where does that leave us?
That's the million-dollar question, right? What we're seeing is that quantum computing isn't just about building faster computers, it's about rethinking the very nature of problems and how we approach them. It's about finding new ways to organize information, manage errors, and design algorithms that work with the quirks of quantum mechanics instead of against them.
So it's not just a hardware upgrade. It's a whole damn paradigm shift.
You got it! And that's why this research is so damn exciting. It's not giving us all the answers, but it's pointing us in the right direction. It's telling us that we need to think differently, be more creative, and really embrace the weirdness of the quantum world if we want to unlock its full potential.
All right, so for those of us who aren't quantum physicists, what's the takeaway here? Why should we give a damn about all this matrix madness?
Because it affects everything. Think about it. More powerful simulations mean faster drug discovery, more accurate financial models, and maybe even a better understanding of the universe itself. It's like, remember when we all thought the internet was just a fad?
Oh, yeah.
This is way bigger than that.
Okay, you've officially blown my mind. So basically, we're on the verge of a quantum revolution.
Yes.
That could change, well, everything.
Exactly, and the best part is we're just getting started.
Oh, God.
There are still so many unanswered questions, so much potential to explore. It's like we've stumbled into a whole new dimension of problem solving, and we're still figuring out the rules of the game.
And that, my friends, is what makes this whole quantum computing thing so damn exciting. We're not just observers. We're active participants in shaping the future of computation. We're pushing the boundaries of what's possible, one mind-bending matrix problem at a time.
Well said. And who knows what incredible breakthroughs await us on the other side of this quantum rabbit hole, right?
That's what I'm talking about. All right, you brainiacs, that's a wrap on this quantum adventure. Go forth and ponder the mysteries of the universe, and we'll catch you on the flip side for another deep dive into the unknown.